The following lecture is one of a series that covers the HNC Electrical Engineering Unit, FY 9E DC and AC Principles. This lecture provides a basic introduction to inductors and presents a number of techniques to analyze inductive circuits that have combinations of series and parallel elements. The subject elements to be covered in this lecture are as listed on this slide. A summary of all the information covered, the worked examples, and a set of self-assessment questions are contained in the accompanying workbook. A permanent magnet exhibits a number of unique physical properties. The first and perhaps the most obvious one is that it is attracted to ferrous materials. Another property is that when freely suspended, a magnet will align itself with the Earth's magnetic field and point north-south. This is the principle of a magnetic compass. The north pole of a magnet is so called as this is the end that points north. The other end by default therefore points south. These properties may be explained by considering the presence of an energy field around the magnet in the form of lines of magnetic flux, termed a magnetic field. The strength of the field is indicated by the extent of the area covered by the lines and by how tightly the lines are packed together. The lines of flux making up the magnetic field about a magnet have three key rules governing their behavior. The lines always flow from a north pole to a south pole. The lines never cross. They can twist and distort, but they never cross each other. Finally, the lines of flux are concentric, that is, they are uniformly distributed about the magnet. From these rules, it is possible to explain the interaction between magnetic poles. Since the lines always flow from a north to a south pole, if two unlike poles are brought together, then the flow lines will link the two poles, pulling them closer together. Hence, unlike poles attract. If two similar poles are brought together, this compresses the fields, pushing the two poles apart. Like poles repel. A magnetic field is produced when an electric current flows through a wire. Looking at the conductor shown in the diagram, the current direction is indicated by the arrows. As the current flows, a magnetic field is produced with the flux lines acting in concentric circles about the conductor. The direction of the flux lines may be determined using the corkscrew rule. If you picture a corkscrew being driven into the conductor in the direction of the current, then the direction the corkscrew is turned indicates the direction of the field. There are two additional symbols used when illustrating the direction of current flow in a conductor. The symbol showing a circle with a cross is used to represent the view looking at the end of the conductor with the current flowing away from the viewer. The cross represents the feathers of an arrow. The symbol showing a circle with a dot is used to represent the view looking at the end of the conductor with the current flowing towards the viewer, the dot representing the tip of the arrowhead. If two current-carrying conductors are run in close contact and parallel with each other, the fields generated by each conductor will interact. Consider the situation where the current is flowing in the opposite direction in each conductor. Using the corkscrew rule, we know that the surrounding fields will be as shown. As a result, the two fields will become compressed in the gap between the two conductors, and the magnetic force will push them apart. Where the currents in the two conductors are flowing in the same direction, the fields are orientated in the same direction, so the fields will merge, resulting in a magnetic force pulling the two conductors together. One method to determine the nature of the magnetic field around a coil is to imagine slicing the coil in half along the axis shown, and then considering the following. The currents flowing through the ends of the coil showing on the A side of the section will all be going down, and the currents flowing through the ends of the coil shown on the B side of the section will all be coming up. Knowing that the fields produced by parallel conductors where the currents are going in the same direction will merge, then by using the corkscrew rule, the fields on the A side of the section will be in the clockwise direction, and those on the B side of the section will be going anti-clockwise. Since lines of magnetic flux always flow north to south, then the right-hand side of the coil must be a south pole, and the left-hand side will be the north pole. The magnetic field that forms around a coil is the same as that of a permanent magnet, and there is a simple rule to determine the polarity of the field, termed the right-hand grip rule. The rule works as follows. Imagine gripping the coil with your right hand, with your fingers going in the direction of the current. Your thumb will then be pointing at the north pole of the solenoid. The following example is in the accompanying workbook, Inductive Circuits, Right-Hand Grip Rule. The diagram shows a coil of wire wound on an iron core connected to a battery. We are required to determine the polarity of the field and sketch the magnetic field pattern associated with the current carrying coil. The longer line of the battery symbol is the positive terminal, so the current is flowing in through terminal A and out through terminal B. So, using the right-hand grip rule, the fingers will curl clockwise about the coil and the thumb will point to the top of the coil. This is then the north pole, and the bottom of the coil will be the south pole. So the lines of magnetic flux will align from the north to the south pole. When a current-carrying conductor is placed in a magnetic field, it will experience a force. This is the basic principle of an electric motor. The two diagrams show different views of a current-carrying conductor lying in and at right angles to a magnetic field. The top view is looking down on the conductor, and the side view is looking into the conductor core. Both pictures indicate the direction of current flow. Looking at the side view, we know that if we have a current flowing out of the board, using the corkscrew rule, there will be an anti-clockwise acting magnetic field about the conductor. There is also the field between the two poles acting from the north to the south pole. Since the two fields cannot cross, they must distort to accommodate each other as shown. In this arrangement, the flux lines flowing under the conductor are in alignment with the flux lines around the conductor and so are enhanced. The flux lines flowing over the conductor are in opposition and will be diminished, resulting in an upward force acting on the conductor. The magnitude of the force depends on 4 factors: the strength of the field between the two poles, termed the flux density, symbol uppercase B, units Tesla; the size of the current flowing in the conductor, symbol uppercase I, units amperes; the length of the conductor lying in the field, symbol uppercase L, unit meters. Finally, if there is more than one conductor lying in the field, then the number of conductors, symbol uppercase N. The force measured in newtons may then be calculated by taking the product of the above 4 factors. So, F equals N times B times I times L. Fleming's left-hand rule provides a method to determine the direction a force will act, or the resultant motion of a current-carrying conductor lying in a magnetic field. Holding the thumb and the first 2 fingers of the left hand at right angles to each other, if the first finger points in the direction of the field, flowing from north to south, and the second finger points in the direction of the current, in this case flowing out of the board, then the thumb will be pointing in the direction the force will act, which will be the direction of motion of the wire. A magnetic field may be defined as a region in which a current-carrying conductor would experience a force. When a supply is connected across the coil terminals, a current will flow, and a magnetic field will form around the coil. The polarity of the coil can be determined using the right-hand grip rule. The direction of the lines of the magnetic flux is shown by the arrowheads, and the strength of the field is indicated by the line density. When a conductor cuts through a magnetic field, a voltage is induced into the conductor. This is the basic principle of an electric generator. The 2 diagrams show a conductor lying in and at right angles to a magnetic field. The top view is looking down on the conductor, and the side view is looking into the conductor core. The side view indicates the direction of motion of the conductor, which in this case is moving up with a certain velocity. The magnitude of the induced voltage depends on 4 factors: the strength of the field between the 2 poles, termed the flux density, symbol uppercase B, unit Tesla; the length of the conductor lying in the field, symbol uppercase L, unit meters; the velocity of the conductor, symbol lowercase v, unit meters per second. Finally, if there is more than one conductor lying in the field, then the number of conductors, symbol uppercase N. The induced voltage may be calculated by taking the product of the above 4 factors. So V equals minus N times B times L times V. The minus sign comes from understanding Lenz's law, to be discussed later. The direction of the induced voltage may be determined using Fleming's right-hand rule. Fleming's right-hand rule provides a method to determine the direction of the induced voltage when a magnetic field is cut by a conductor. Holding the thumb and the first two fingers of the right hand at right angles to each other, if the first finger points in the direction of the field, flowing from north to south, and the thumb points in the direction of motion of the wire, then the second finger will point in the direction of the induced voltage, which in this case is acting out of the board. Lenz's law states the polarity of the induced voltage is such that it always serves to oppose the action producing it and is denoted by a minus sign. As the conductor cuts up through the magnetic field, a voltage will be induced in the conductor in the direction shown using Fleming's right-hand rule, and a current will flow. So we now have a current-carrying conductor lying in a magnetic field, which will experience a force which, using Fleming's left-hand rule, will act in a downward direction, opposing the very motion that was creating the current. This is Lenz's law. To understand how a voltage is induced into a coil, consider the circuit shown. When the switch is closed, a current will start to flow and a magnetic field will start to build. While the field is building, the flux is cutting the coils and inducing a voltage, which by Lenz's law will be in opposition to the source. Once the field is fully established, the flux will no longer be cutting the coils and the induced voltage will disappear, at which point the only thing limiting the current will be the resistance of the coil. Consider the circuit shown where the magnetic field around the coil is being maintained by a steady current flowing through the coil. When the switch is opened, the magnetic field will start to collapse. As the field shrinks, the flux starts to cut the coils and induces a voltage, which by Lenz's law will attempt to maintain the current and so will be in the same direction as the source. Once the field has fully collapsed, the induced voltage also disappears. Self-inductance is the ability of a coil to induce a voltage in itself as a result of a changing current. The symbol associated with inductance is the letter uppercase L, and its unit is the Henry, abbreviated to the letter uppercase H. An inductor is represented in a circuit diagram by the symbol shown. The magnitude of the induced voltage will depend on the size of the inductor and the rate of change of current. There is a relationship between induced voltage, the inductance, and the rate of change of current. The highlighted box shows the induced voltage is equal to the size of the inductor times the rate of change of current. Provided the inductance is in henries and the rate of change of current is in amperes per second, then the voltage calculated will be in volts. The minus sign in the formula indicates that the induced voltage will be in opposition to the supply producing it. Lenz's law. The following example is in the accompanying workbook, Inductive Circuits, Inductance. Here we are required to determine the magnitude of the induced voltage in a 20 millihenry coil if the current changes from 2 amperes to 7 amperes in 25 milliseconds. We know the induced voltage is equal to the size of the inductor multiplied by the rate of change of current. The minus sign is generally ignored when carrying out the calculations. So the change in current, delta I, is equal to 7 minus 2, which equals 5 amperes. Note, it is the size of the change that is important, not the direction. It doesn't matter if the current was increasing from 2 to 7 or decreasing from 7 to 2. The change is still 5 amperes. And the time taken, delta T, is equal to 25 times 10 to the power minus 3 seconds. So, VL equals the inductance times the rate of change of current. Substituting the values, VL equals 20 times 10 to the power minus 3 times 5 divided by 25 times 10 to the power minus 3, which equals 4 volts. A series circuit is one in which all the elements are connected nose to tail. So, in the circuit fragment shown, the 3 elements L1, L2 and L3 are all connected in series. Inductors connected in series sum in a similar manner to resistors in series. An equivalent of the series circuit may therefore be drawn where inductors L1, L2 and L3 may be replaced by a single inductor, Ls. The highlighted formula shows that where there are a number of inductors connected in series, they may be replaced by an equivalent inductor, Ls, where Ls is equal to the sum of the individual inductors. The following example is in the accompanying workbook, Inductive Circuits, Series Circuits. Here we are required to determine the total inductance of the series circuit. So, Ls equals L1 plus L2 plus L3. Substituting the values, Ls equals 1 plus 2 plus 3, which equals 6 henries. A parallel circuit is one in which the noses of all the elements are connected together and all the tails are connected together. So in the circuit fragment shown, the 3 elements L1, L2 and L3 are connected in parallel. Inductors connected in parallel sum in a similar manner to resistors in parallel. An equivalent of the parallel circuit may therefore be drawn where the inductors L1, L2 and L3 are replaced by a single inductor, Lp. The highlighted formula shows that where there are a number of inductors connected in parallel, they may be replaced by an equivalent inductor, Lp, where the reciprocal value of Lp is equal to the sum of the reciprocal values of the individual inductors. The following example is in the accompanying workbook, Inductive Circuits, Parallel Circuits. Here we are required to determine the total inductance of the parallel circuit. The reciprocal of the total inductance of a parallel connected circuit is the sum of the reciprocals of all the individual inductors. Substituting the values, 1 over LP equals 1 over 1 plus 1 over 2 plus 1 over 3, which equals 1.83, which is the reciprocal of LP. So LP equals 1 over 1.83, which equals 0.546 henries. As a current flows in an inductor, it stores energy in the form of a magnetic field, energy that will be recovered when the magnetic field collapses. Consider the circuit shown. When the switch is closed at time 0, a current will start to flow, which, while it is increasing from 0 to some maximum Is, will generate an opposing voltage in the coil, Lenz's law. Once the field has been fully established, the current will no longer be changing, so the voltage across the inductor will be 0, and the inductor ceases to draw power from the supply. Looking at the chart, this process happens over a period of time, t seconds. The power consumed over this time is given by the formula P equals V times I. However, the average value of current flowing through the inductor during that time will only be half the final circuit current, so I will equal I over 2. The voltage across the coil during that time depends on the size of the inductor L and the rate of change of current delta I divided by delta T. From the chart, it can be seen that the change in current is simply I and the change in time is T. So the voltage over the period T equals L times I divided by T. Substituting these values for voltage and current back into the power equation, P equals L times I squared divided by 2T. Since energy equals power times time, if we multiply L times I squared divided by 2T by T, the T's cancel, and we get the result shown in the highlighted box. Energy stored equals a half times L times I squared. Provided the inductance is in henries and the current in amperes, then the calculated energy will be in joules. The following example is in the accompanying workbook, Inductive Circuits, Energy. Here, we are required to find the energy stored in an 18 millihenry coil if the current flowing through the coil is 5 amperes. We know energy stored W equals a half times the size of the inductor times the current squared. Substituting the values, W equals a half times 18 times 10 to the power minus 3 times 5 squared, which equals 225 millijoules.